Hello and welcome to another video in this series as we journey from the very simple primes to the foothills of one of the most important open questions in mathematics, which is the Riemann hypothesis. Today we're going to be looking at a really interesting new proof that the sum of the prime reciprocals diverges, that it grows to infinity. It's based on one from Ivan Niven, which was published in 1971. As I say, the paper itself, the article that was published in a mathematical journal, is really short. I think it kind of fits in less than half a side. So it's kind of short, it's kind of fun. It just moves a little bit faster than the one we looked at before. I'll include a link to that paper. It's open access, so you don't need to log in or have any kind of password to kind of access it, or you don't need to pay at all. I'll include that in the description, but you'll also see it in the blog that accompanies these videos as well, so you can see it yourself. And actually here's a reproduction of it, and that's it. It's just that, it's just a few lines. I think there's about 10 or 11 lines, and just two kind of lines of equations, I guess. But as you can tell from looking at that, there's more to it than first meets the eye. So today's video is about going through this in a slower way, so that we can kind of appreciate what's going on. Right, so before we dive into the proof, there's two things that we need to understand before we can kind of unlock the meaning of the proof. And both of those are really easy. There's nothing to be worried about at all. The first one is this idea of square-free numbers. And the idea is that you can write any counting number, any integer, as a unique product of a square, j squared, and a square-free factor, let's call it k. Now this looks similar to what we've said before about any integer, any whole number, being able to be written as a unique product of primes, and this is where this idea comes from. So let's see why. So any integer, any whole number, is a unique product of primes. We've looked at that before, and if you need a reminder or if you're not sure, do go back to those previous videos and the previous blog articles that talk about that. So any number can be broken down, decomposed into a unique list of primes that are multiplied together, the prime factors. It's actually called the fundamental theorem of arithmetic, and it sounds grand because it is that important. The idea is simple, but it is important. We can split these primes into two groups. We can put together those that are raised to an even power and group those together, and because they have an even power, we can write the whole thing as a square, and I'll write that down with a pen and paper in a minute so you can see. And that leaves us with the other group, which have primes only raised to power 1. Let's look at some examples, and then actually I'll use pen and paper to illustrate this idea in case it doesn't make sense. For some people it's really intuitive, and for others it's not. So this idea of breaking things down, so 360, previously we've just written it as 2 times 5 times 2 times 2 times 3 times 3. Break it down into prime factors. We've done that a few times now. What we've done here is we've grouped them together. So this one would be 2 squared and 3 squared, which together can be written as something squared, and the rest only have a power 1. So the square-free factor is 10, 2 times 5, and the square factor is 36, 6 squared. Let's look at another example, 30, which when you break it down into prime factors is 2 times 3 times 5, and there's no higher powers, so the square free factor is 2 times 3 times 5, and there's no squared factor, so this number is called square free. Actually, let's now draw some pictures just to show that. So if I have a number, I can write it down as, I don't know, prime 1 times prime 2 times prime 3 times prime 4, let's just say. and this one might be raised to the power 2, and this one might be raised to the power 2. This is easy to say, to group. We can group this as P1, P2, and then P3, P4 squared. So this is the squared part, and this is the square free part. Let's see what happens if actually this was 4. Then that would be P3 squared times, and then the whole thing squared. What if this was 5? If that was 5, we would have P4 times P, so we'd end up with part of that P3 coming here. So P3 to the 5 is P3 to the 4 times P3 to the 1, the only one power, and that is the bit that ends up there, and this is the bit that ends up in here. So you can see we can always separate into a squared part and a square free part. I hope that kind of makes sense. It just follows from the fact that we can do a prime decomposition and then separate the ones that just have a power 1. And this example here has shown what happens when we have a high power like 5. We actually split those primes into this group with the even powers, and then the other group with only power 1. Great, so now we've understood what a square free number is. It's a number where all the prime factors have only one power 1. There's no square or higher powers of those primes. Now this might look scary, but it isn't, I promise. All we're doing is looking at this inequality. We're saying something times something equals or is more than or equal to something. Let's look more closely now. Let's kind of hold our breath and kind of look closely at what we're multiplying. Over here we're saying we're multiplying this series. Actually, this series is the sum of square free integers less than n. So it's just the square free integers less than n in this series. And in this series is the squares less than n. So we can write them out. And if we do, and if we multiply them, we're combining those terms. And guess what we're doing? We're combining a square free integer with a square. And we're doing that in all the combinations that we are allowed to do here by the fact that the integers, these numbers will be less than n. If we do that, we make the integers again, all the normal integers less than n. Because we've seen in the previous slide how every integer can be written as a product of a square free factor and a square factor. Can you see what we're doing there? Let's draw a picture in case that's not clear. So let me list these square free integers. 1 by convention, plus 2, plus 3. Now 4 isn't because it's 2 squared. 5, so the primes obviously are. Now 6, 3 times 2. Yep, there's no squares in there. 7, 8 isn't because it's 2 times 2 times 2. So it's got 2 squared in there. And so on. Now that's the square free integers. That was the 1 over k's. Now we're multiplying that by the squares. So it's 1 plus 2 squared plus 3 squared plus 4 squared plus so on. And you can see when we multiply, let me pick a different colour. What we're going to be doing is picking all the combinations of these terms and so on. So all of these are combined with all of these, and we'll end up with a square free factor times a squared. And we've already said that we can write m equals that, so 1 over m is that. Now that's where that relationship comes from between the integers and their squared free and squared factors. Why is there a more than or equal? Well, if you did actually write it out by hand, you'd see that by multiplying these out, we'd end up with more combinations, more terms than there are in the m less than n. So yes, it does generate those integers, but we always end up with more terms. In fact, the equality only happens when you have n is 2. Beyond that, we get more terms. If you're not convinced, try it out by hand. In fact, let's do one now. Let's say n is 3. So we want k and j less than 3. So we want n is 3. And in the square free terms, we want 1 plus 2 plus, we don't want to do 1 over 3 because we want it to be less than 3, times the squared. So 1 over 1 squared plus 1 over 2 squared. If we multiply that out, we get 1 over 1 plus 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed. And that is more than or equal to this sum over 1 over m. M is less than n, which is 1 over 1 plus 1 over 2. So these ones are the extra terms. Great. Now here's a little bit of magic which I really like. So despite this looking really horrible, all it's saying is this thing times this thing is more than or equal to this thing. Now, as n goes to infinity, this becomes the harmonic series 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, which we have seen several times now, diverges. We've also seen the Basel problem 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. That converges, doesn't diverge. And you'll remember it becomes pi squared over 6. So some things times a convergent sum equals a divergent sum. What does that mean? It means this thing must diverge. We can't have this convergent. And that is magic, because it's told us straight away that the sum of the inverse square free integers, 1 over k, diverges. That's really easy. I know we've talked a lot and used lots of words, but some people will be able to just look at that and see that straight away. But some of us, like me, need to be guided a little bit. But actually, we didn't do a lot of work at all, and straight away we can come to quite a powerful conclusion there, that the sum of the inverses of the square free integers, 1 over k, diverges. Magic. So we're going to use that later. We're going to keep that in our back pocket. So let's dive in. And this proof, like so many we've done, is a proof by contradiction. So we start off with something that we suspect is false. And it probably will turn out to be false, but let's make the assumption. Let's assume that the sum of the inverse primes, which some people call the prime harmonic series, let's say it converges to a finite value. Let's call it beta. So we're making that assumption, and we could be wrong, but we're starting with that assumption and seeing where it leads us. If it leads us to something that's a contradiction, then we know this is wrong. Right. Now the next statement is really simple. All it's saying is, if we have a sum to infinity, if we chop off the sum at a point like p less than n, the n is the cutoff point, then that's going to be smaller than the full series as long as all the terms are positive. And we know they are because they're over the form 1 over prime. So that's just saying, instead of saying 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 5 plus 1 over 7 for all the primes, we cut it off at a certain point. that clearly will be less than the full series. So that's the statement almost of the obvious, but it's written in a mathematical way. Now the next step is saying the same thing. So e to the power of beta, that one, is more than e to the power of this thing which we cut off. That's that. It's funny how these symbols look overwhelming, but actually when you talk a little bit about them, you can suddenly see that they're actually not scary at all, and we can see what that was. We're just saying that the full sum is more than the partial sum, and e to the full sum is therefore more than e to the partial sum. Now e to the sum of something can be turned into a product. Let's see why. So when we have something like x raised to the power a plus b, that's the same thing as this product x to the a times x to the b. So in our case we have e to the something a plus b, what is it, some sum, a plus b plus something, let's say plus c, plus dot dot dot, equals the product of e to the a times e to the b times e to the c, and so on. So we've turned this into a product. That's where that comes from. So e to the 1 over p, going over all the primes. So that looks like we've made a big leap, but we haven't. It's just using that simple fact there. And in case you haven't seen that before, I'm sure you have, this symbol looks like a big pi, but it means product. So this sigma means sum, and this means product. We are going somewhere with this. It might look like we're just doing this for fun, but it's going to come to a nice conclusion. Let's do another cutoff. We know the Taylor series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial. We can chop it off. We can chop it off at the second term, so we can say e to the x is always more than 1 plus x. So that's, again, looks like we've made a big leap, but all we've done is just use the idea that part of a sum is less than the full sum as long as all the terms are positive. And that means this e to the something, e to the x, is going to be more than 1 plus x, 1 plus something. Does that look too much? Let's write that out. So we know that e to the x is 1 plus x squared, or 1 plus x, sorry, plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And if we chop it there, 1 plus x, we know that e to the x is more than 1 plus x, and that means e to the 1 over p is more than 1 plus 1 over p. That's what we're using. Not difficult at all. It just takes time to kind of, once you see it, it's easy. You just need someone to help you see it. Well, I need someone to help me see it. So that's what we've got there. We've just said e to the 1 over p is more than 1 plus 1 over p. Now if we multiplied out this sum, this term 1 plus 1 over p, we multiplied it out over lots of primes less than n, all the primes less than n, what you'd find is that the terms that combine 1 over p, well, in fact any of the terms, there's no way to combine the same prime twice. All the powers of p are just 1. Let's see that in action. So let's just take a simple example. 1 plus 1 over 2, that's the first prime. 1 plus 1 over 3 plus 1 plus 1 over 5. Just take the simple example, and that's going to be 1 plus a half plus a third plus 1 over 2 times 3, and then 1 plus 1 over 5. And then multiplying that out, you can already see the combinations are either the single primes or more than one prime, but it's P1 times P2. There's never a P1 squared or a P2 squared. Let's continue with this to see it. Is 1 plus a half plus a third plus 1 over 2 times 3. That's because of this one. And now the same thing again, plus a fifth of it, so it's 1 over 5 plus 1 over 2 times 5 plus 1 over 3 times 5 plus 1 over 2, 3, 5. And you can see there's never a 2 squared or a 3 squared or a 5 squared. It's just not going to happen. If you extended this out, you could see, if you wanted to put in the work, you'd see that. And that's important because what it means is all these denominators are square free. So multiplying out the product gives terms that look like 1 over k, where k is square free. We've demonstrated that. And that's because each prime contributes to any k at most once, by virtue of the way we multiply out. So, again, if we did that multiplication, we'd end up with more terms than the number of k less than n. So we've got on the left hand side here 1 plus 1 over p for p less than n. If we multiply that out, yes, you would get 1 over k, 1 over a square free factor, a square free number, but you'd end up with more terms. So you'd have these but extra ones. And again, the equality only happens when n is 3. Yeah. So let's put everything together. We're almost there now. This is almost the final slide. Putting everything together, we said that beta was, we were going to assume that beta was the finite sum of the inverse primes. We were assuming it went to we assumed it converged, and now we were saying e to the beta is more than the sum of 1 over the primes for p less than n, because the full sum is more than the partial sum. We saw how we could convert this into a product, and then we use a Taylor series to say this is more than the product of 1 plus 1 over p. And then we said actually that generates more terms than 1 over k, the square free numbers. Okay, so that's saying this is more than this, because this is a strict more than. So let's take a step back. We know that this thing diverges. We've shown that already at the earlier point in this video. So what we've found, what this is telling us, is that as n goes to infinity, the finite value e to the beta is greater than this thing, which is divergent. We know this is divergent. We know this is convergent, or we assumed it was. But that's a contradiction. Our assumption was wrong. Beta isn't convergent, and therefore the sum of the inverse primes, the prime harmonic series, diverges. So what I've done here is written out that key line in Niven's proof that starts from the assumption and jumps to almost a conclusion. And I'm just going to explain each leap at each of these steps, just as a review of what we've done. So we start off by saying that beta was the sum of the inverse primes, and we were assuming it converged to beta. Now, this full sum to infinity is always more than a partial sum, which cuts it off at a certain point. So that's why it's more than the partial sum, p is less than n. So instead of going up to infinity, it's stopping. And what we've done is we've just raised it. So e to that, and e to that. And that's more than. Great. Now, we've turned this sum, this e to the sum of several things, into a product by using x to the a plus b is x to the a, x to the b, and if we had plus c, that would be x to the c. So you can see this sum in the power becomes a product, and that's why we can say product of e to the 1 over p, p is less than n. That's what this thing here is. So that's equal to that. Now we've used the Taylor series of e to the x is 1 plus x plus something something something. We've chopped it off at that point, therefore we can say it's more than there. So this product, that is more than that. And then when we multiply out all these terms, we find that the terms are of the form 1 over k, where k is square free, because there's no way to combine the same prime more than once. It's always 1 over p1 times p2, or 1 over p1, p2, p3. It's never 1 over p1 squared or p2 squared. So it gives these terms, and it's more than, because we always generate more terms than are in this series. And we showed earlier that that diverges. So if that let me change colour. So if that diverges, and this thing we assumed was convergent to beta, the sum of 1 over p, that's a contradiction. So this assumption, because this is saying this is more than this, it's saying this is more than a divergent object, so that's wrong. That means this one, that means the sum of 1 over p diverges. Fantastic. I hope you enjoyed that. See you next time. Bye.